Hello, in this video, I'm going to show how to solve this problem involving an electric field and a square surface. Okay, so we're trying to find the electric field through this or rectangular surface that's length L and intersects the z-axis at H, and it intersects the x-axis at A. The electric field is written right here. It's some amount in the z direction and some amount in the x direction. So we can kind of like think of it as pointing out like that. Try that again. Like that. So we want to find the flux of that electric field through that surface. Okay. So the flux is equal to the integral of E dot dA, the area, over the surface. Okay, so dA is the normal vector, so we can think of the normal vector up here as the vector perpendicular to the surface. And this electric field, in general, will not be perpendicular to the surface, so we will need to perform that dot product there. So the first thing I'm going to do is I'm going to find the normal vector. So this n hat is going to be a unit vector, meaning a vector of length 1 that is normal to this surface. Okay, so to write out that unit vector, I'm going to write it as n hat is equal to, well, it's going, if A were bigger, it would point more in the z direction. If H were bigger, it would point more in the x direction. And you can think of this triangle, say this triangle, here, or let's draw a line going directly in the z direction, and this over here. That triangle is similar to this triangle here. They both have angle theta here. So we can write n hat as basically the portion that's in the z direction is proportional, is like the A, and the H is like the portion that's in the x direction. So we can write this as n hat is H over square root of A squared plus H squared, and that's in the x hat direction, plus A over the square root of A squared plus H squared in the z hat direction. This, the hypotenuse down here, A squared plus H squared, we're going to be writing that a lot in this problem. So whenever you have something that you write a lot, it's handy to define a new variable to equal that quantity. So you can do this. You just write let H equals the square root of A squared plus H squared. So if you're solving a problem, it gets complicated and you don't want to rewrite something over and over again, you can just, write let, define a new letter. We're using capital H, just kind of picked a letter out of the hat. And we'll use that to signify square root of A squared plus H squared. So using that notation, n hat is equal to H over capital H plus A over H z hat, like so. Okay, so we have the normal vector. Now it's time to do the integral. So we're trying to do this integral here. Phi is equal to integral over the surface. So let's back up and remember what our surface is. So our surface is that big area here. So I'm going to do a double integral. The surface is going to be a double integral, one over this length and one over this length. So we can imagine dividing up this surface into a bunch of little squares. they're going to be dy long on that side as you go in the y direction. But this other side is not in the x direction, it's in the slanted direction. So I'm going to make a new variable called w that increases as you go from here to here. So we can write this double integral as, well, we're going to integrate from 0 to L dy, and we're going to integrate from 0 to, from here, this will be w equals 0 here, down to here. That distance there is h. Remember this h, this capital H is this thing we defined as the square root of a squared plus h squared. That's the hypotenuse line there. So we can define that as the length of the hypotenuse. So w needs to go from 0 to the full hypotenuse. We'll call that dw. And then inside here, we're going to need e dot dA. Well, the dw dy is the area part of area without the direction. This is the magnitude of the area. We need the direction. So the direction we're going to write as n hat. So n hat dw dy, that whole thing there is dA vector. And then what we have over here is E. Okie dokie. So the next thing I'm going to do is I'm going to plug in my N and plug in my E. So phi is equal to integral from 0 to L, integral from 0 to H of E, which is E naught, big parentheses, x plus y z hat plus x hat dot into n hat, which is, we've already said, is h over capital H x hat plus a over capital H z hat dw dy. Okay, when I multiply these together, if I take an x hat times a z hat, that gives 0, because the dot product between those two, they're 90 degrees from each other, they get 0. Same with the z hat and the x hat. So the only ones that are survive is when I take z hat with z hat and x hat with x hat. Each of those will give 1 times the two factors that are getting multiplied together. So I can simplify this whole thing. If I do that, I'm going to pull the E naught out front because it's a constant. I get E naught 0 to L, integral 0 to H. If I simplify that all out, I'm going to get x plus y a over H. That's from the two z parts, and then I'm going to get plus x h over y, or sorry, h over h d w dy. This part right here is from the x hat parts. Okay. So now we just got to do an integral. Actually, there's one little bit we need to do before we do the integral. The integrand, this thing inside here, has x's in it, but x is a function of w, right? As you change x, so you go in the x direction, or as you go in the w direction, you go in the w direction, you change x. If you go in the x direction, you change w. They're related to each other. How are x and w related? Well, they are related by x is equal to w times a over h. How did I know that? Well, if you look at the picture here, w has a bigger distance to go than x. So while x only changes by a, w changes by the hypotenuse L. So I just multiplied the ratio. When w is 0, x is 0. when W is H, X is A. So that's what that equation gives you. If I plug that in for my X's, and I'm also going to do some rearranging, then I'm going to get phi is equal to E naught integral from 0 to L, integral from 0 to H. Well, I'm going to pull the X's together and turn them into a W, A over H, and I get W A plus H over capital H squared plus Y A over H dW dy. Okay, now you might have noticed that this term right here has only W's in it, and this term right here has only Y's in it. So when we can split these two integrals up, when we do the L integral of this term, we get L of a constant. An integral of a constant from 0 to L is just going to give L. We do the W integral of this guy from 0 to H, we're just going to get H. So we can rewrite this as phi is equal to E naught times quantity. So the first one, we're only going to have a W integral on, and we're going to have an L out front. L integral from 0 to H of W A plus H over H squared dW, plus the second one, H is going to come out front, and we're going to have the integral 0 to, that's an integral sign, integral to L of Y A over H dy, like so. So now I just need to do the integrals. This bit here is a constant. This bit here is a constant. So I can do that. Actually, this H cancels with that H, as it turns out. So I can write this as phi is equal to E naught. We get L A plus H over H squared. All that constant comes out. I get the limit. So integrating W, dW gets W squared over 2, W squared over 2 from 0 to H plus A. Same thing here. Integral Y dy gives Y squared over 2, 0 to L, like so. You put in those limits, and when you put in 0, nothing happens. When you put in H here, this H kills that H. You put in this L here, it just becomes L squared. Right, this is phi is equal to E0 times L A plus H times 1/2 plus A 1/2 L squared. We can pull an A and an L out, and we get phi is equal to E naught L A times I just realized something. I switched H's back here. This should be little h, little h, little h, like that. Okay. Sorry about that. Okay, so when I pull that out, then I get, oh, and I can also pull out a 1/2. Both of the terms have a 1/2, so I can pull out a 1/2 as well. 1/2. I get an A plus H plus L. And that's the answer. Let's do one quick check. The units of this, we have length times length times length. So length cubed times E naught is 5. But what is E naught? E naught, remember, E naught comes from the E equation here. E naught, well, if E, the electric field, has units of would be E. What are the units of E? Well, E is equal to newtons per coulomb. That's what the definition of electric field is. So if E is newtons per coulomb, E naught would be newtons per coulomb divided by meters, because X is in meters. So E naught, if E is in newtons per coulomb, E naught is in newtons per coulomb meter, as it turns out. So if we use that for E naught down here, we get newtons per coulomb meter times meters cubed. So we get newtons per coulomb times meters squared. Phi is, the units of phi are electric field times area. So newtons per coulomb times meters squared. So the units work out, and that's that. You can check, you can see most of this work here is just doing a big long integral. You could do that with a computer as well. Basically, the problem is mostly done when you get to here and you've plugged in X for W A over H. After that, it's just all doing calculus to get to there. Okay, so that's how you solve that problem.